Binkley, and my project is developing high internal phase emulsion to improve the storage stability of lutein. I started this project during the fall semester and have been working under Dr. Libo Tan of the Department of Human Nutrition, and my graduate advisor is Yanqi Zhang. So in my project, I first hope to introduce high internal phase emulsion and convey its significance. I will then explain our goals and how we were able to conduct these experiments. And later, I will describe the results and how they'll be used in future testing. So my project centers around a compound known as lutein. Lutein is a dietary antioxidant that is a main component of macular pigment, which is found in cells of the eye. Dark green leafy vegetables are great sources of lutein, which include kale, spinach, and broccoli. Lutein can also be found in other foods, such as egg yolks and corn. Now, lutein is critical in neonatal visual development and helps prevent eye diseases. However, there are many challenges to using lutein. One is that it has a very low bioavailability. Only about 10 to 15% of it can be absorbed. Lutein also has a low storage and thermal stability. We want to create a way to increase lutein's bioavailability through a safe and effective design. And one way of doing this is through the use of high internal phase emulsion, which is a novel encapsulation technique. Now, we all know that water and oil do not mix. However, an emulsion allows the mixture of two liquids that are normally immiscible. A high internal phase emulsion has a minimal internal phase ratio of 74:5. And for our purposes, this just means that 74% of what we mix will be the lutein and oil. This method can be used to increase the bioavailability of lutein. We are unique in that no other studies have used high internal phase emulsion to carry lutein. So our objective is to increase the storage stability of lutein, and we will do this through the use of OS starch as a stabilizer. OS starch is a commercially available modified starch. Starch itself is safe for human consumption and is cost-effective, so it's great for our purposes. This is how the bioavailability of lutein will be increased, as you can see in the diagram on the right. The OS starch represented by black wavy lines will increase the lutein and oil. So for my experiment, I tested the lutein retention of two different starches, CTA starch and HC100 starch. But first I had to create samples for testing. I created biopolymer solutions ranging from 10 to 30% concentration of starch and water. I then pipetted 2.5 milliliters of this and 7.5 milliliters of oil mixed with olive oil, or lutein mixed with olive oil, in a glass tube, and this means that my mixture will be 75:5. I then homogenized the sample for 2 minutes at 20,000 RPM. So I need to make sure that the resulting mixture is homogeneous and gel-like, which is shown in these samples. And from here, I'm able to do my measurements. So first I compare their visual appearances. We kept each sample in a sealed glass tube at room temperature over a week. During the duration of this week, we want to make sure the samples remain homogeneous and gel-like. To show the samples were gel-like, I turned the tubes upside down. So as you can see circled through the week, only the 25% and 30% CTA samples remain gel-like. It is also noticeable that some of the samples separate their biopolymer solutions from the lutein and oil. As you can see, the arrow points to the 20% solution on day 7, which has a dark orange layer lying over the emulsion. The same can be seen in the HC100 samples. As shown in the circle on day 7, the 20% sample remained gel-like during the entirety of the week. Some of the samples, such as the 30%, showed a separation in the mixture as early as day 0. A dark orange layer lies over the emulsion, showing it has gone through a great amount of degradation and has a low amount of stability. And for this reason, I did not use it in any future testing. So in addition to observing their visual appearances, I conducted a test for their stability, which was done on days 0, 1, 3, 5, and 7. I pipetted 1 microliter of emulsion and 5 milliliters of THF into a glass tube. To create the mixture, I vortexed them for 5 seconds and then homogenized them for 12. After this, I centrifuged the samples at 25 degrees Celsius for 8 minutes at 3,000 RPM. So once they were ready, I measured the absorbency using a UV-Vis spectrophotometer. And from here, I'm able to calculate lutein retention. Lutein retention as a percentage is the amount of lutein after treatments divided by the amount of lutein before treatments times 100. So from these calculations, we are then able to analyze our results. The graph shows lutein retention in CTA starch as a percentage over 7 days. As you can see, the lutein retention on day 0 was set at 100%. On day 7, we can see that the 10, 15, and 25% samples demonstrated a great amount of stability. A similar analysis can be done with the HC100 starch. Each of these samples remained relatively stable, with the 10 and 15% samples showing the most stability. So along with the stability test, we can test each sample's microstructure using the fresh samples from earlier. This is completed through the use of confocal laser scanning microscopy, or CLSM for short. The green color is due to the fluorescence of lutein. Now, recall from earlier that the OS starch will encapsulate the lutein in oil after a successful emulsion. If this emulsion remains successful, then we will see the lutein in oil pictured in very small dots. So as you can see in the 10% CTA, there are large splotches of oil which are unhomogenized droplets, which did not remain stable. However, as we increase the solution of starch, we can see that a larger number of small dots is pictured, indicating a greater amount of stability and less degradation. The same trend is seen in the HC100 samples. So in conclusion, all the samples remained relatively stable. It is also clear that each of our observations supported one another. For example, each of the results of the 25% CTA indicated a good emulsion. The physical sample was homogeneous and gel-like on day 7. The microstructure pictures many small dots, which are the encapsulated lutein, and there is a high lutein retention percentage. So based on these results, we hope to duplicate this testing and/or test over a longer period of time to ensure more accurate results. For this testing, I was able to use any part of the emulsion, and in the future, I will use specific areas to test for individual bioaccessibility. Now recall from earlier that lutein is essential in neonatal visual development and help prevent eye diseases. Our focus is to inhibit an eye disease known as retinopathy of prematurity, or ROP. This is why the results from the emulsion and the lutein retention percentages are significant. Since starch is safe for consumption, we will introduce these emulsions to RP-induced neonatal rats in order to test the bioavailability of lutein and to see if it is successful in inhibiting ROP. Thank you, and are there any questions?
How may the lutein retention of a certain sample exceed over 100%?
So when I pipette an emulsion, I have to make sure that I only get part of the emulsion. As you can see in some of the samples, the solution separated, so you have the emulsion and the lutein and oil. And if I pipette that concentrated lutein and oil, then I won't be able to know how much was in the emulsion separately, so that will increase the concentration.
So are there any other biopolymer alternatives that could be used to encapsulate lutein?
Yeah, so oil and water emulsions are very common. However, they're used with encapsulation techniques and ingredients that are not safe for infants. So that's why we use starch. But in terms of what starch we use, we have used many different starches. However, I chose to test these because they were the most successful through our other testing.
If the lutein retention rate in the rats proves to be high enough, what are the next steps for this project?
Yeah, so if we see that the lutein actually inhibits ROP, then we can actually recommend this to clinical research and to find a way to possibly use lutein as a treatment to help with visual development in infants.
How does the emulsion itself lead to higher bioavailability?
So the free lutein itself is very hard to absorb. That's why it has a low bioavailability, but the emulsion allows an encapsulation of the lutein. It helps carry it so that we're able to absorb it better.